In this lecture, we will talk about how to obtain the natural frequencies of a circuit from a given formulation. Okay, namely the node formulation, mesh formulation, and the state equation. So suppose that we're given, or perhaps we obtained ourselves, node formulation for some certain LTI circuit. Okay. That is node admittance matrix times node voltage vector equals the right-hand side, where the right-hand side contains the inputs, okay, namely independent voltage sources, voltages, and independent current sources, currents, and perhaps the initial conditions, okay, if we have some integral terms within the node admittance matrix. And from this obtain determinant of y of s. Now this is necessarily a square matrix, okay. Now replace d, operator d, our derivative operator, with the complex variable s, okay. Obtain this matrix of s and then obtain this determinant, which will give you, okay, this form. A ratio of two polynomials, a numerator polynomial dividing a denominator polynomial. Okay, so numerator polynomial is denoted by num s, and we have the denominator polynomial. Now, if you remember our example from the previous lecture, we computed this determinant and we obtained just a single polynomial, okay. In other words, our, so to speak, denominator polynomial was 1. Now it turns out that denominator polynomial could be of degree 1 or larger, okay. In the previous, in our case, in our example, it was of degree 0. It could be degree 1 or larger when we have, okay, when we have some integral terms in our formulation. In other words, denominator polynomial appears when we have integral or d inverse terms. Okay. Now, again, if you go back to our example, we didn't have any integral terms in our node formulation because our circuit in the previous lecture didn't contain any inductors. Okay, if you're doing a node formulation and if you have no inductors in the circuit, then you will not have any integral terms. Likewise for the mesh formulation, if you have only inductors in your circuit, once again you will not have any integral terms. Okay, so once this determinant is put in this form, numerator polynomial divided by denominator polynomial, all you have to do to figure out the natural frequencies is to check, to find the roots of the numerator polynomial. Okay, so the natural frequencies of the circuit are the roots of the numerator polynomial. Okay. Now the dual case is not surprisingly true for the mesh formulation, so let's also put that down. Okay, suppose you have a circuit and then you chose to formulate it in terms of mesh currents, and you obtain all the equations and finally you put them in matrix form. So what you obtain therefore is some square matrix that's a function of the operator d multiplying your vector of formulation variables, your vector of unknowns, the mesh currents, and we have the right hand side. okay, VMS, which contains the terms associated to the initial conditions and also the inputs. Again, what you do is, from that formulation, you obtain or you write down the determinant of this matrix Z of S, Z being the mesh impedance matrix, and put it in this form. Numerator polynomial divided by the denominator polynomial. And once again, the natural frequencies of your circuit are the roots of the numerator polynomial. Okay. Natural frequencies are the roots of the numerator polynomial. Okay, and finally, we have the state equation or state formulation. Okay, where our formulation variables are a certain set of capacitor voltages and certain set of inductor currents. And the equation or the formula of equation that we obtain in the end of our formulation has this form: x dot, let me write it here, x dot equals ax plus bw. X dot equals ax plus bw. And now, how about natural frequencies for this formulation? Again, let's put the equation, this equation, in this form. Some matrix of the derivative operator d multiplying the vector of unknowns, and then we have the right hand side. This equation is not in that form, but can be put easily in that form. Remember that this dot is no other than derivative with respect to time, therefore we can write state equation as this. So that looks more familiar or more close to the node equation, mesh equation, and then we collect all the unknown terms or the state terms on one side, and we write dx minus ax equals bw, and then we write this as di minus ax equals bw, where w is our input vector. Now, the state equation put in this form looks exactly like the form of the mesh formulation or the node formulation. Okay, some matrix of operator d multiplying the vector of unknowns, and then we have the right hand side. So again, for that form, all we have to do is compute the determinant of Si minus A. Okay, so let's do that. Obtain determinant of Si minus A. Okay, this is called the characteristic polynomial of the A matrix, and because of because how we formulate the circuit using state equation, the integral terms never appear in state equation. Okay, and therefore this determinant, unlike the determinant here or determinant here, will never contain a denominator polynomial, or denominator polynomial will be just 1 of degree 0, and therefore all you have to do is check the roots of that characteristic polynomial d of s. In other words, natural frequencies of the circuit for which you have the state equation are the roots of determinant of Si minus A. And those roots have a special name associated to the matrix A. They're called the eigenvalues of the A matrix. Okay. Note that we don't say the natural frequencies of the circuit with respect to node formulation, or natural frequencies of the circuit with respect to mesh formulation, and so on, because natural frequencies should be well, they are independent of the formulation choice. Okay, so whatever method that you apply, whatever formulation you go with, you should always obtain the same set of scalars here for the natural frequencies of the circuit. But there's a subtlety that we have to be careful about. So let us try to see that through a simple example. Okay, let's put that as a remark. The natural frequencies depend only on the circuit. Okay, that is, they are independent of how you formulate the circuit. Of the formulation choice. But okay, whenever you have some integral terms, okay, in your node formulation or mesh formulation, not that we have no such problem with state formulation, okay, so whenever you have integral terms with node formulation or mesh formulation, in other words, whenever you have a denominator polynomial of degree 1 or larger, perhaps, then some of the natural frequencies may go unnoticed, okay, may not be detected through computing the roots of determinant, the roots of numerator polynomial. Okay, so let's see that on a simple example. Okay. Here we have two capacitors connected in series. Okay. And there's a resistor connecting them. And suppose this is V1, C1. This is C2, V2. And here we have the current I, the mesh current. Okay? Now, for this circuit, let's find the natural frequencies using the mesh formulation. Okay. Okay. So it seems very. It seems like the right choice to apply. That is the applying mesh formulation, because we have just a single mesh. Okay. Therefore, we will write just a single equation. Okay, we will have just a single unknown, and it seems it's the best way to go. It's the easiest way to go. Okay, so with mesh formulation, okay, this is our only mesh, and suppose this is our mesh current I in clockwise direction. What we do is we write KVL here. Okay, so starting from this point, what we have is minus V1. Okay, because we're going in that direction, and minus V1 is minus V10. Okay, minus 1 over C1, and then you integrate the capacitor current, which is in that direction. Okay, and then capacitor current is minus I. Therefore, we can replace that minus with plus, and we have the inverse I. Okay, so that's minus V1. Then we have Ri, and finally we have V2, which is V20 plus 1 over C2. And then you integrate I2, and I2 is I. And by KVL, that should equal 0. Okay, now, therefore, we have the following mesh equation after throwing the initial condition terms to the other side. (1 over C1 plus 1 over C2 times the inverse. We have an integral term here, and we have another integral term here. We combine the two. Plus, we have an r multiplying I equals, we throw the initial condition terms to the other side. Okay, we have V1 0 minus V2 0. Okay, so in this case, this is our Z of t, mesh impedance matrix. But since we have just a single formulation variable, this matrix is a 1 by 1 matrix. In other words, it's a scalar. Okay, now let's compute determinant of Z of s. From there, pull the numerator polynomial and check its roots. Okay, determinant of Z of s equals 1 over C1 plus 1 over C2, 1 over S plus R. Now, since Z of s is 1 by 1, determinant of that exactly equals itself. Therefore, we're here talking about Z of s. Now, let's put this Z of s into numerator polynomial divided by denominator polynomial, which can be easily done. And what we have is Rs plus 1 over C1 plus 1 over C2 and divided by S. And this is our numerator polynomial divided by denominator polynomial 4. Okay? Now, our method tells us to take this numerator polynomial and find its roots. Now, this is a first order polynomial, therefore it has a single root, and it's clear where that root is. Root of numerator polynomial is, we have just a single root, let's call it S1, and S1 is at minus 1 over R times 1 over C1 plus 1 over C2. Okay, and this, according to mesh formulation, is the only natural frequency of the circuit. But there seems to be a problem, okay? And the problem is the following. Now, we have two dynamic components, and we can choose the initial conditions, those two initial conditions, arbitrarily, okay? There's no constraint by KVL or KCL or something else that prevents us from choosing V1 0 what we like and then V2 0 what we like. Since the degree of freedom is 2, this circuit is of second order. Okay, so that means it should have two natural frequencies. But mesh formulation gave us only one of them. Okay, so in order to figure out that missing natural frequency, therefore, we have to resort to a method that does not contain integral terms. And that method, that fail-proof method, is the state equation. Okay, so let's find natural frequencies, this time by state formulation. Okay, state formulation. Now, we need to choose a state, and in this case, it's very easy what we should do. The state is V1, V2, namely the capacitor voltages. Now, for this state, let's obtain the state equation, namely x that equals AX plus BW. Now, clearly, since we have no input in the circuit, the state equation will simply be x that equals AX. Now, let's figure out that A, and then check the eigenvalues of that matrix. Okay, which should be the natural frequencies of the circuit. Okay, so let's write node equation here and also node equation here. What we have here is C1 V1 dot, this current, the capacitor current, equals this plus this current equals 0 by KCL. Okay, plus V1 minus V2 over R equals 0. Do the same thing here. C2 V2 dot, this current second capacitor current, plus this current equals 0, which is V2 minus V1 divided by R, okay, equals 0. And from these two node equations, we can easily obtain x dot equals AX. How? Okay, let's collect dotted terms on one side, and we have therefore V1 dot equals minus 1 over R C1 V1 plus 1 over R C1 V2. Okay, all we did is we rewrote this equation. Let's do the same thing to the second equation. V2 dot equals 1 over R C2 V2, excuse me, V1 minus 1 over R C2 V2. Okay, all that remains is to put these two equations into x that equals AX form, which is very easy. X that equals, this is our A matrix. Okay, now x that equals AX. Once again, we don't have any BW term because we don't have any W. The circuit is input free. Okay, for the first row, let's look at the first equation, V1 dot. V1 is our first state variable. Okay, here we have minus 1 over R C1, and here we have plus 1 over R C1. For the second row, we look at the second equation. Here we have 1 over R C2, and here we have minus 1 over R C2. Okay, and our formulation is complete. Once we have a state formulation, natural frequencies directly follow from the fact that they are the eigenvalues of the A matrix. So let's compute the eigenvalues of A matrix, which clearly are 2, because A is a 2 by 2 matrix. Okay, and then we will have the entire list of the natural frequencies of the circuit. In other words, we will find the missing natural frequency that we were unable to detect with mesh formulation. Okay, so let's compute the characteristic polynomial, in other words, determinant of Si minus A. So that equals S plus 1 over R C1 minus 1 over R C1 minus 1 over R C2, and S plus 1 over R C2. Okay, this determinant is this times that minus this times that, and that equals, after cancellation, S times S plus 1 over R C1 plus 1 over R C2. Okay, this is our characteristic polynomial. Once we have the characteristic polynomial, all that remains is to check its roots. And in this form, it's clear where the roots are. One is at the origin at 0, the other is at minus this term here. Okay, roots of the characteristic polynomial d of S, S1 equals minus 1 over R, 1 over C1 plus 1 over C2. Note that this root we were able to detect using mesh formulation. Okay, but the second root, let's call it S2, the second eigenvalue at the origin, it went undetected by the mesh formulation. Okay. This mode goes undetected by mesh formulation. Okay, so the lesson that we should take from this example is the following. When we have integral terms, we should be careful, and if we have state equation, there's nothing to worry about. In particular, node and mesh formulations okay, if they contain integral terms may sometimes fail to show, to catch the natural frequency at the origin. Which is exactly what happened with this circuit when we apply mesh formulation to it. Had we chosen node formulation, we would have run into no problem, because since we have no inductors in this circuit, in node formulation, there will appear no integral terms.